Hi everyone. In this lesson we're going to cover inner product spaces. Now an inner product is a concept that you add on top of a vector space. So it's an additional property that we add on to a vector space, and we'll define it precisely soon. Now before we do that, let's recall from your study of vectors in calculus that if we're given two vectors u and v in R3, or this also works in R2, the dot product between the two vectors u and v is defined to be this quantity. So we say u dot v equals u1 times v1 plus u2 times v2 plus u3 times v3. So we simply take the components of the vectors, multiply them together. So for example, multiply u1 and v1 together, do the same thing for u2 and v2, and then just add, and then also u3 and v3. Now if we were working with vectors in R2, we just wouldn't have this last piece right here. So that's how we defined a dot product in R3 or R2. Now this can be generalized to vectors in Rn like this. So if we're given two vectors, u and v, in Rn, well, we just generalize this very easily to be u1 times v1 plus u2 times v2 plus dot 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 plus un times vn. So this number that we get would be u dot v. Now if we're given this definition, take note of what we have down here. We can write the norm or length of a vector in terms of this dot product. So if you recall before how we defined the norm of a vector, right here's our norm, we defined it as the square root of u1 squared plus u2 squared plus dot 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 plus un squared, and we interpreted this as being the length of the vector. Well, notice that that is just the square root of u dot u, because after all, if we have a u dot u, for example, take a look at this right here. If this v right here is the same as u, then this is just going to be u1 times u1, well that's u1 squared, plus u2 times u2, and that would be u2 squared, plus dot 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 plus un times un, and that would be un squared, and we would get this right here. So the norm or length of a vector is simply the square root of u dot u. Alright, and also take note that we have this other property for norms. If you take a scalar c times u, and you take the norm of that vector, you can actually move the c outside the norm symbols, but you have to put absolute values around them. So this quantity is equal to the absolute value of c, the scalar c, times the norm of the vector u. And you can easily verify this just by what you would do is up here, in each of these terms you would have a c squared multiplied against each of these terms up here. That's what the left-hand side right here would be. And then you would just factor out the c squared, and you would get the square root of c squared times the square root of u1 squared plus dot 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 plus un squared. And this quantity right here is the absolute value of c, and this quantity right here is just the norm of u. So you see you can very easily verify that. Now let's take a note about the distance between 2 points in Rn, and we've already worked with this previously, but let's just review it here. So if you're given 2 points in Rn, P and Q, then you can interpret those 2 points, P and Q, as being two vectors. Just call it P with a little arrow over it, Q with an arrow over it, so two vectors. Then the distance between P and Q is going to be the length of the difference vector Q minus P. And we write q minus p. Notice how we write it here as pq. We think of this vector. We think of this vector as having its base at the tip of p and then pointing towards the tip of q. So that's what this dotted vector right here would be. So this would be the vector pq, which is q minus p actually. Have to be careful with your ordering. Now actually this vector doesn't really live here. Remember, it actually lives here where its base is at the origin, so it points like this. So this is where it actually lives. And so the distance between the tip of the two vectors p and q is the length of this vector, and so it's just going to be the norm or magnitude of q minus p. So let's take a look at this example. So in this example, we want to determine if the following 3 points, P, Q, and R, that we have listed here, are collinear, meaning do they all lie on a single line? So the way we're going to handle this is we're going to think of these points as forming a triangle, like we have pictured right here. So you see right here in this picture, we might have the point P right here, the point Q here, and the point R right here. And so this vector right here, pointing from Q to P, would be P minus Q. This vector would be R minus P, and this vector would be Q minus R. Now, to determine if these 3 points actually lie on a single straight line, what we're going to do is evaluate the length of the sides of the triangle here. And if, for example, this side right here is exactly equal to the sum of these two sides, well, then the points must be collinear. In other words, this R, it would actually have to look like this. You would actually have to have a situation like this, where the P would be here, the Q would be here, and the R would be right here. You see, in this case, the length P minus Q would then exactly equal R minus P, that distance, plus Q minus R. So if this holds, if we have equality right here, then the 3 points actually have to be collinear. So we just need to calculate the length of these 3 sides and see what we get. All right. So down here we have those lengths calculated. So let's see, right here if we look at P minus Q, that's going to be this quantity, -2, -4, -6. P minus R, now I have P minus R here instead of R minus P, but that doesn't matter. When we're taking the length of these vectors, it doesn't matter which direction the vector is pointing in when we take the length. So this quantity is -4, -8, -12, and R minus Q, I have that one backwards from the drawing too, but it doesn't matter when we look at the lengths. That's going to be 2, 4, 6. So if we evaluate the length of these 3 vectors right here, what we get is the magnitude of P minus Q is 2 root 14. You can verify that. Just take the square root of -2 squared plus -4 squared plus -6 squared. You'll get 2 root 14. The magnitude of R minus Q is 2 root 14. And the magnitude of P minus R is 4 root 14. And so we see that the magnitude of P minus Q plus the magnitude of R minus Q equals the magnitude of P minus R. So these points must be collinear. And the way that I have it set up here, it actually turns out then that this point right here it turns out that the P minus R is actually the longer side here, so this might actually be P, and this would actually be R, and then this would actually have to be Q here. And actually this point Q is actually like right here. It's actually on this line between P and R. So these 3 points are collinear. Now here we have a theorem detailing some properties of the dot product. So if we're given two vectors u and v in Rn and any scalar k, then the following properties hold for the dot product. So you notice that the dot product is commutative. U dot v equals v dot u. You have a distributive property for the dot product, so u dot v plus w equals u dot v plus u dot w. So you can distribute this u to the v and w. And then you have an associative type of property with respect to the scalar k. So k times u, now this means scalar multiplication of k against the vector u, dotted with v equals u dot k times v, or k times u dot v. So you can move the k around like that. You can either group it with the u or the v, or you can completely move it outside. We also have the property that u dot u, u dotted with itself, is always bigger than or equal to 0, and u dot u is equal to 0 if and only if u is actually the 0 vector. So down here we have the proof of these properties. Let's take a look at a few of them. For example, number 1 is fairly easy to prove, the commutative property. So if you take a look at u dot v, notice that that's going to be u1 times v1 plus u2 times v2 plus all the way out to un times vn. Now all of these multiplications going on here are with respect to real numbers, so you can flip them around because real number multiplication is commutative. So we can rewrite this term as v1 times u1 plus v2 times u2 and so on. And you get that this quantity right here is v dot u. With respect to the distributive property, the proof of that goes like this. Notice that u dot v plus w, if we start out with the left-hand side, that's simply this right here. So you notice we have each component being multiplied like this. So u1 times v1 plus w1 plus u2 times v2 plus w2 and so on. And now, of course, real numbers have a distributive property here because this is just real number multiplication right here, and this is real number addition. And so we can rewrite this term like this. Just distribute the u1 to the v1 and w1, and we can do that for every term. And then just combine terms down here. You notice that we combine all of the u1 times v1, u2 times v2, so all the u times v's are grouped together here. And over here we have all of the u times w terms grouped together. And of course this term right here is just u dot v, and this term over here is u dot w, and that proves number 2. Also keep in mind when you're going through this, it gets a little bit tricky. This addition right here actually means vector addition, okay? And this addition right here actually means real number addition. So these two plus symbols right here actually represent different operations. And that's why sometimes if authors want to be crystal clear about which addition is which, sometimes you'll see this written as maybe like plus with a little box around it here. But I don't have that written out in this case. Now the proof of 3 is very similar to the proof of 1 and 2. So if you look at KU dotted with V, that's going to be like this right here. Now keep in mind this dot right here, I put a dot here, but that actually, I could have left that out. That means real number multiplication here. K times U1 times V1. This is all real number multiplication here, as is this over here and this over here. So we can move these around as follows. Actually we're going to factor the K away from each term here. So notice that's what we have down here. The K has been factored out. And keep in mind this dot here actually means real number multiplication between U1 and V1, U2 and V2, and so on. And we end up with the fact then that this is just K times U dot V. Okay, this, what I have underlined here, is just U dot V. Okay, so that proves this equality, and the case, and proving that U dotted with K times V is also K times U dot V is similar. And so you can conclude that all of these are the same. This, and this are all equal. Okay, so that proves number 3. And then the proof of number 4. Just notice that U dot U, U dotted with itself, is this quantity right here. It's U1 squared plus U2 squared plus dot 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 all the way out to UN squared. Now, of course, this term is going to be bigger than or equal to 0 because every UI squared is bigger than or equal to 0. So, of course, U dot U has to be bigger than or equal to 0. And also, if U dot U is equal to 0, well, then each of these terms, UI squared, must be 0. All of these terms right here must be 0. And so that means U has to be the 0 vector. And similarly, if U is the 0 vector, then all of these terms are 0. And so you get U dot U being 0. So therefore, U dot U is 0 if and only if U is the 0 vector. That's what we've argued up here. We've argued that if this holds, then U is the 0 vector, and if U is the 0 vector, then U dot U is 0. Now let's take note of this important theorem here. This is going to tell us how we can calculate angles between vectors in any vector space, whether it's R2 or R3 or any other vector space. So this is a very important result right here. So if you're given two vectors U and V, now first of all we're going to consider them to be in R2 or R3 first. Then U dotted with V is actually the magnitude of U times the magnitude of V times the cosine of the angle formed by the two vectors. So to prove this result, consider the following graphic down here. So what we have here is we have two vectors. This is the vector U. This is the vector V right here. Now the length of this vector right here is the magnitude of U. Okay, so this is your vector U right here. And its length is magnitude U. This arrow right here is the vector V, and the length is the magnitude of V. This vector right here is, that's going to be U minus V. Now really, remember, it actually lives over here, but we have it drawn right here. And the length of this side of the triangle is magnitude of U minus V. Alright, so what we have here is a triangle with the lengths of each side labeled. And notice that this angle right here between U and V we will label as being theta. Now, by the law of cosines, we have this result down here. Now this may be a strange form. You may have seen this written in a different form, maybe like this. If I labeled this side A, the length of that side is A, and the length of this side of the triangle is B, and the length of the side opposite theta, C, you may have seen this formula down here written as C squared equals A squared plus B squared minus 2AB times the cosine of the angle theta. Okay, that may be the form that you're more familiar with by labeling the sides of the triangle here A, B, and C. But in our case here, A is the magnitude U, B is the magnitude of V, and C is the magnitude of U minus V. So we're going to use these variables, or these notation, instead of A, B, and C. So what we have here by the law of cosines is that magnitude of U minus V squared, that's C squared, equals magnitude of U squared, that's your A squared, plus magnitude of V squared, that's your B squared, minus 2 magnitude U times magnitude V times cosine theta. So that's 2AB cosine theta right here. Okay, so that's how it relates to this formula right here that you're probably more familiar with. Now, what we're going to do is this. Let me just move this down here. Okay, now what we're going to do, recall that the magnitude of a vector is squared is equal to U dot U. Okay, that's a result that we had previously. Okay, so from this equation right here, then we have that the magnitude of U minus V squared, notice that that is U minus V dot U minus V. And U minus V dot U minus V, we can evaluate that as U dot U minus 2 U dot V plus V dot V, right? That's what you get when you simplify this. You follow a distributive property. U dot U minus U dot V minus V dot U plus, because of the two negatives being multiplied, V dot V. And you end up with this right here. Also, magnitude of U squared is U dot U, and magnitude of V squared is V dot V. So plugging this in here, this in here, and this in here, what we end up with is this equation down here. And you notice that U dot U, they cancel, V dot V, they cancel, and so you end up with negative 2 U dot V equals negative 2 times this quantity. Cancel the negative 2's, and you end up with U dot V equals magnitude U times magnitude V times cosine of theta. And that proves our result. Now from this result, we have some very important definitions that follow now. So first of all, note this. Suppose U and V are non-zero vectors in either R2 or R3. Then notice from our equation, U dot V equals magnitude U, magnitude V times cosine of the angle between them, that if U and V are perpendicular to each other, meaning the angle between them is pi over 2, then we end up with the fact that U dot V equals magnitude U times magnitude V times cosine of pi over 2, or 90 degrees. Well, this term right here is 0. And so we end up with the fact that U dot V is 0. And similarly, if U dot V is 0 to start with, suppose we had two vectors where U dot V is 0, then that means that this term has to be 0. And if magnitude u and magnitude v are non-zero, that means that the cosine of theta right here, would have to be 0, which means that theta must be pi over 2. So if u dot v is 0, then the angle between the vectors is 90 degrees, or pi over 2. So therefore we end up with the result that u dot v is 0 if and only if the angle between the vectors is pi over 2, or 90 degrees. And so what we do then is we create this following definition, and we actually generalize this for all vectors in Rn. We then say that if we take two vectors u and v in Rn, we say that they are orthogonal. That's the word we use instead of perpendicular for general vectors. So they're perpendicular or orthogonal if u dot v is 0. So that's our definition for orthogonality of two vectors in Rn. So we say two vectors are orthogonal, meaning perpendicular, provided that u dot v is 0. Let's take a look at this example. Oh, and also notice one other thing here before we look at this example. From this definition here, technically the 0 vector, if for example v is 0, you're always going to have u dot 0 is 0 for any vector u. So the 0 vector is technically orthogonal to every vector in Rn. That's a result of this definition here. So let's take a look at this example here. So if we're given that u is the vector 2, 3, 1, that's in R3, and v is the vector -1, 2, -4, let's verify that they are orthogonal vectors. So all we have to do is take the dot product, u dot v. All right, so that's going to be 2 times -1, plus 3 times 2, plus 1 times -4. And when we add all this up, we get -2 plus 6. So that's 4 minus 4. Yep, we get back 0. So therefore u and v are orthogonal or perpendicular. Now notice another fact from our formula that we had here. If you start out with this formula that we derived, you can take this and calculate the angle theta between the vectors u and v if you simply divide the magnitude u times magnitude v under the u dot v and then take the inverse cosine function of both sides. And you end up with this formula down here. Take note. So this tells us how we can calculate the angle between two vectors. It's simply the inverse cosine of u dot v divided by magnitude u times magnitude v. So if we evaluate this quantity and then take the inverse cosine, that'll give us the angle between two vectors. Now that is provided, of course, that the denominator here is non-zero, right here. Okay, right here we have to have this non-zero in order to do this. Now, there's one important thing to note here, though. We really only verified this formula right here for vectors in R2 and R3. So, you see, in order to take the inverse cosine, we have to verify that this quantity right here for vectors in Rn satisfies this inequality down here. You know, in order to take the inverse cosine of something, like this is the something I'm talking about, this has to be between -1 and 1. Now, we only verified this for vectors in R2 or R3 from our graphic that we had. So what we have to do is verify that this inequality here actually holds for all vectors in Rn. And it actually does. We will verify that later on. In fact, we're going to verify this for any vector space, and eventually we'll generalize this notion of a dot product, and we'll eventually call it an inner product. So we will prove that this is true for all of Rn, and in fact for other vector spaces as well later on. So what we can do then is we can actually use this as a definition for the angle between vectors in any Rn, not just R2 and R3. And so let's take a look at this example. So here let's find the angle between these two vectors. 1, 1, 1, 1, now that's in R4, and -1, 3, 2, 0. Both of those vectors are in R4. Alright, so we have to use this formula right up here. So we have to calculate u dot v. Alright, well, let's see. U dot v here I claim is 4. You can verify that. 1 times -1 plus 1 times 3 plus 1 times 2 plus 1 times 0. That'll give you back 4. The magnitude of this vector is just going to be the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. That's going to be the square root of 4. You can verify that the magnitude of this vector is the square root of 14. That's the square root of -1 squared plus 3 squared plus 2 squared plus 0 squared. So that'll give you back the square root of 14. And so therefore the angle between these two vectors is going to be the inverse cosine of u dot v divided by the magnitude of u times the magnitude of v. If you evaluate this quantity, the arc cosine of 4 divided by the square root of 4 times the square root of 14, you should find that it is approximately 1.007, and that's going to be in radians. You could convert that to degrees if you wanted, but normally we always work in radians. And so there you go. That's how you can use this formula right here to calculate the angle between vectors. Now here we have a definition that is going to generalize the notion of a dot product to any vector space V, and we're going to call it an inner product now. So an inner product on a real vector space is a function that associates a real number, denoted by this quantity, with each pair of vectors u and v taken in your vector space V, in such a way that the following properties hold for any two vectors u and v and scalar k. So these are the four properties that must hold for an inner product. So the first property is a commutative property. The inner product of u with v is equal to the inner product of v with u. We have a distributive property. The inner product of u with v plus w is inner product of u with v plus the inner product of v with w. And then we have an associative type of property with respect to the scalar k. The inner product of ku with v is the same as, we can move the k with the v, the inner product of u with kv, or we can move the k outside and say it is just k times the inner product of u with v. And then we also have to have that the inner product of u with itself is always bigger than or equal to 0, and the inner product of u with itself is equal to 0 if and only if u is actually the 0 vector. And so any vector space that has an inner product on it, we then call an inner product space. Now take note that the dot product automatically satisfies all of these conditions because of the previous theorem that we looked at. Remember, we verified all of these properties for the dot product. If we just denote the inner product of u with v as u dot v, right, then all of these properties hold for the dot product. That was a previous theorem that we looked at. So the dot product is a special type of inner product, and that's what we have defined down here. So just take note that Rn forms an inner product space with the inner product defined by the dot product, like this, and we call that the Euclidean inner product. So just take note of that definition. Let's take a look at an example here. So let's consider the space of all continuous functions on the closed interval from 0 to 1. That's what this represents. So this is the vector space of all real-valued continuous functions with the standard notion of addition and scalar multiplication. We had seen this previously and verified that it was a vector space. Let's verify that this notion right here of an inner product actually satisfies all four properties of an inner product. So the inner product of f with g is just the definite integral from 0 to 1 of f times g. Notice that this will give us back a real number r. So we have to verify all four of those properties hold. Let's first of all verify the commutative property. Well, the inner product of f with g is the integral from 0 to 1 of f times g. Well, this right in here just means regular number, real number multiplication, so we can flip the f and g around like this, and we end up with the inner product of g with f. So the inner product is commutative. Let's verify this property right here. So f plus g, the inner product of f plus g with h, that is going to be the integral from 0 to 1 of f plus g times h. And since this is all real number multiplication and addition, we can write this as this down here. And then we can split up the integral as follows, here and here. And you notice that this is the inner product of f with h plus the inner product of f with g. And you'll notice here that I actually have this written a little differently from the property, but it doesn't matter. The original property that we had was written like this. But it doesn't matter if we write it like this or like this. Doesn't matter which way we write it here because of the commutative property for the inner product, property number 1. And what we have proven here is actually this one right here instead of this one. But it doesn't matter which one we use, because if this one is true, then this one will be true. And if this one is true, then this property will be true by the commutative nature of the inner product. Now let's take a look at property number 3, verifying that. So if we look at the inner product of k times f with g, that is simply this right here, where we multiply all three together. Now this dot means real number multiplication. And so by properties of the definite integral, we can move that k outside, like this, and we get that this quantity is equal to k times the inner product of f with g. So that proves property number 3. And also note if the k were with the g, we would still get the same result down here. Now for property number 4, Just note that if we look at the inner product of f with itself, that's equal to the definite integral from 0 to 1 of f times f, which is the integral from 0 to 1 of f squared. Now this is always going to be a positive function. Its graph will lie above the x-axis, so of course this quantity is bigger than or equal to 0. And also notice that the inner product of f with itself is equal to 0 if and only if f is the 0 function, because of these two results that we have right here. If f is equal to 0, so if we go in this direction first, if f is equal to 0, then clearly the integral from 0 to 1 of f times f is 0. So the inner product of f with itself is 0. And if the inner product of f with itself is 0, well, then that means that this must hold. And the only way this can hold, the only way the integral from 0 to 1 of a positive function can be 0, is if that function itself is identically 0. And that, of course, is for a continuous function. So therefore, the inner product of f with itself is equal to 0 if and only if f is the 0 function. And that verifies property number 4. Let's take a look at another example of an inner product. So now we're going to consider the vector space R2 here. So in R2, let's verify that this quantity, so if we take the inner product of the vector u and v and define it to be 1/9 u1 times v1 plus 1/4 u2 times v2, keep in mind we're letting u and v be vectors of this form, so u is u1 comma u2, and v is defined similarly, so we define the inner product of u with v to be this quantity right here. Let's show that this defines an inner product, and this is going to be called a weighted inner product. So you notice it's a little different from the dot product. If this 1/9 and 1/4 were both equal to 1, we would just have the regular dot product. So what we're going to do here is just verify this result right here and leave the rest as exercises. So if we look at the inner product of u plus v with w, well, that's just going to be this quantity right here, 1/9 u1 plus v1 times w1 plus 1/4 u2 plus v2 times w2. And that is equal to this quantity right here. If we distribute the w1 with the u1 and the v1, we get this right here and this. And then just move things around a little bit, and you'll get this plus this. You notice we just grouped u1 w1 and u2 w2 together right here. And v1 w1 is over here, and v2 w2 is right here. And we get this result. So that verifies that the inner product of u plus v with w is the inner product of u with w plus the inner product of v with w. Now let's take a look at this example. So here we're going to look at an example of inner products that are generated by matrices. This is going to be a slight generalization of the example that we just looked at. So let's consider the vector space Rn and let A be any n by n matrix. Let's show that the inner product of u with v, defined as taking the matrix A times u, and remember this is going to be a vector, we're going to take the dot product of it with the vector A times v. So instead of u dot v here, we first let the matrix A act on u and v. We get two vectors back, then take the dot product of those two vectors. Let's verify that this defines an inner product. And then for part B, thinking of u and v as being n by 1 column vectors, let's show that the inner product can actually be written as u transpose A transpose times A V, where all of this means matrix multiplication, or you could actually write it like this as well. We're just going to verify the first one right here. And then for part C, let's find the matrix that generates the inner product defined in the previous example. All right, so for part A, we're going to verify that U plus V, comma W equals the inner product of U with W plus the inner product of V with W. Remember once again that that is the same as what we had stated in the definition. I just have it a little backwards here, but it doesn't matter which one you use. Remember U with the way it was stated in the definition was actually like this. So I actually had these sort of backwards a little bit here, but it doesn't matter. This is equivalent to this one right here. Okay, so keep that in mind. All right, so if we look at U plus V with W, well, by definition, that is going to be this right here. And by the distributive property for matrices, we can write that like this. So notice we distributed the A with the U and V. And then by properties of the dot product, we can write this right here as AU dotted with AW plus AV dotted with AW, and this is UW plus VW. And there you go, we just verified it. All right, now let's take a look at part B. So let's notice here that if we write U as a column vector and V as a column vector, then notice that if we look at U dot V, remember that's going to be U1 times V1 plus U2 times V2 plus dot 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 plus UN times VN. Well, we can actually write that as U transpose times V, where this right here means matrix multiplication. Remember, if we take the transpose of U, that would turn it into something like this. That would turn it actually into a row vector. This is the transpose of U right here. This is U transpose. And then if we did matrix multiplication with V1, V2, and so on like this, okay, now this isn't a form where we can just do matrix multiplication. We take this row times this column, and you get U1 times V1 plus U2 times V2. In other words, you're getting the dot product. Okay, so we see that we can write the dot product of U with V as just U transpose times V. So what we then have is, if we look at this, AU dot AV, that's just going to be AU transpose times AV, where this is now all matrix multiplication. And A times U transpose is going to be U transpose times A transpose, and then times AV. And we have just proven the result that we wanted. So AU dotted with AV can just be written as U transpose A transpose times A times V. And that's it. And remember, we use the fact here that A times B transpose, when you multiply two matrices, you get back that is equal to B transpose times A transpose. So just keep that in mind. Now let's take a look at part C. We wanted to find the matrix that generated this inner product down here, like this. Well, notice that this inner product right here, if we let A be this matrix, 1/3, 0, 0, 1/2, notice the 1/3 is the square root of 1/9, and the 1/2 is the square root of 1/4. So this quantity is actually equal to all of this right here. Notice if we multiply these two matrices together, we get 1/9, 0, 0, 1/2. And if we multiply that by v1, v2, like this, we are going to get back the vector 1/9 v1, 1/4 v2. And then if we hit that on the left with the matrix u1, u2, like this, you get back u1 times 1/9 v1 plus u2 times 1/4 v2. In other words, you're getting back this right here. Okay, so that's what we had to do there. So that verifies that the matrix that generates this inner product, this weighted inner product right here, is this right here. Now we have listed here some important properties of the inner product. So if you take three vectors, u, v, and w, from any inner product space, then we have these results. The inner product of u minus v with w is the inner product of uw minus the inner product vw. So you have a distributive property with respect to the minus here. Now once we prove part A, part B follows immediately because of the commutativity property of the inner product, the fact that uv equals vu. And then part C is an important property. If you take the inner product of the 0 vector with any other vector v, that is equal to the scalar 0. And because of the commutative property, this is of course the same as the inner product of v with the 0 vector. Let's take a look at the proof of A and C. So here's the proof of part A. If we consider the inner product of u minus v with w, recall that from our study of vector spaces that negative v is equal to the scalar -1 times v. Okay, so that's by this theorem. So we can write u minus v as u plus -1 times v, comma w. Now we can apply the distributive property with respect to this plus right here. So we get that this is equal to the inner product of uw plus the inner product of -1 times v, comma w. Now we can move this -1 in front of the inner product. That is a property that inner products have. And so we get this line. And then of course these are both just real numbers here. And so we can write this as the inner product of uw minus the inner product of vw. And there you go. Now for the proof of part C, let's note that for any vector u, u minus u is of course the 0 vector. So what we can do is we can write then that the inner product of 0 with any other vector v is equivalent to u minus u, comma v, right, where this is equal to 0, the 0 vector. And then using part A, we can break it up like this. And of course, you have the same number here as you do here, and you're subtracting, so you get back 0, and there you go. And so that's exactly what we wanted to prove. And by the commutative nature of the inner product, this is true then as well. Now let's recall this. We're going to study the norm in inner product spaces and the distance between vectors in inner product spaces. So recall that in Rn, we denoted the norm of u, the norm of any vector u, to be this quantity. So remember that this is u dot u to the 1/2 power. Right, u dot u giving you back u1 squared plus u2 squared and so on. All right, so we can then, if we realize that the dot product is itself an inner product, notice that we can then write the norm of u is equal to, so here we have what we just wrote, and u dot u is an inner product, so let's write it like this. So this gives us an idea of how we should define the norm of a vector in an inner product space. So we should just define the norm of any vector u to be the square root of the inner product of u with itself. And that's exactly what we're going to do. As for the distance between two vectors, recall that with respect to the Euclidean norm, the distance between two vectors was defined to be this quantity. We just subtract the two vectors and take the length of the difference vector. That's what this is. And this quantity, just like up here where this is equal to the norm of u, this is going to be u minus v dot u minus v to the 1/2 power. And we can write that as the, recalling that the dot product is an inner product, we can write it like this. And so this gives us an idea of how we should define the difference between two vectors, the magnitude of the difference between two vectors in an inner product space. This is exactly how we're going to define it. And so this discussion leads to the following definition that we have here for the length of vectors and distance between vectors in any inner product space. So we've simply defined the norm or length of a vector in an inner product space like this right here. So the norm of u is equal to the square root of the inner product of u with itself. And as for the distance between two vectors, we simply define the distance like this to be the norm of u minus v, and that is equal to the inner product of u minus v with itself to the 1/2 power. And that's it. So that's how we define the norm and distance in a general inner product space. Let's take a look at this example now. So here we're going to consider the vector space of all continuous functions on the interval from -1 to 1 that will form a vector space. And we are going to define the inner product like we did before with a prior example. The inner product of f with g is going to be the definite integral from -1 to 1 of f times g. And we verified before that this is indeed an inner product. And we want to evaluate the norm of the function x squared, and then we want to find the distance between x squared and x, those two functions. Alright, so we first want to evaluate the norm of x squared. So let's do this down here. Now notice I have a square right here. That just makes our notation a little bit easier, and then we'll take the square root of this quantity right here once we evaluate it. It just makes it a little easier to go through these steps here instead of having everything like this all raised to the 1/2 power. Notation just becomes a little cumbersome. So let's evaluate the norm squared of x squared. So that's just going to be the inner product of x squared with itself. And by definition, that's the integral from -1 to 1 of x squared times x squared, which of course is the definite integral from -1 to 1 of x to the 4th. And you can easily evaluate that right here. Antiderivative of x to the 4th is x to the 5th over 5. Evaluate that from -1 to 1, and you'll get 2/5. And so therefore the norm or length of the function x squared is the square root of the inner product of x squared with itself, which is the square root of 2/5. And so that is our answer. It might seem a little bit strange to think of the length of a function or the norm of a function as being a number like this, but that's what it turns out to be because of our definition of this inner product. And as for the distance between x squared and x, we just have to evaluate the norm of x squared minus x, which is the inner product of x squared minus x with itself to the 1/2 power. And so that's going to be this right here. So notice we have the definite integral from -1 to 1, x squared minus x squared, because we're multiplying this by itself 2 times. And then we raise all that to the 1/2 power. And so you can evaluate the definite integral here. You can evaluate what's in here pretty easily, of course. It's just a polynomial. And you'll find that you get 16/5, and then you need to just take the square root of 16/5, and so you'll get 4 over root 15. And that's your answer. Now let's take a look at this theorem. This is called the Cauchy-Schwarz inequality. This is an extremely important inequality in mathematics. This is one of our more important inequalities right here. So it makes a statement that the absolute value of the inner product of u with v is less than or equal to the length of u times the length of v. Now if you think back to a prior result that we had, this should make sense if you think about dot products. Remember that we had this result, u dot v equals magnitude u like that. Recall that result? Well, if we take the absolute value of both sides here, this is always going to be positive anyway, so we just get this. Now the cosine of theta, that's always less than or equal to 1, right? So we have this result, which looks exactly like this, except we have the dot product. Well, the dot product is an inner product, okay? And so this, we can see this result right here directly from this one. Now that's not a proof, of course, because this result is only true. We only verified it for the dot product. We didn't do it for any general inner product. So that's why we have to go through this proof right here. All right, so let's take a look at this proof. This is one of the more elegant proofs in mathematics that you'll see. It's it's sort of a little bit tricky, but it's very elegant. All right, so to prove this right here, we're going to start out as follows. We're going to let t be any real number. And by the requirement that the inner product of u with itself is bigger than or equal to 0, well, we then have this result. So the inner product of tu plus v for any two vectors u and v, the inner product of tu plus v with itself is bigger than or equal to 0. Now let's break this inner product up using the distributive properties for the inner product, and what you get is this right here. Okay, so it's just sort of like a FOIL method, right? The inner product of tu with tu plus the inner product of tu with v plus the inner product of v with tu plus the inner product of v with v. That's exactly what we have here. Sort of like the FOIL method when you're multiplying a plus b squared. Now what we can do is pull the t out from here and here, and we'll get two t's on the outside, so that'll be t squared right here. So we get u, the inner product of u with itself times t squared, plus we actually have two of these right here. So if we move the t out in both of them, we'll have 2t times the inner product of u with v, plus, and then we have this vv right here. All right, so now let's think of this guy right here as being an a. This term right here, the 2uv, let's think of that as being a b. And let's think of this as being a c. And so we end up with the equation at squared plus bt plus c is bigger than or equal to 0. All right, so what we have now is, let's take a look at the solution to this. Now we're going to set it equal to 0. Okay. Now, because this equation is bigger than or equal to 0, what that means is that the graph of it, if you were to graph it, it either looks like this, where it lies completely above the x-axis, or it dips down and maybe touches the x-axis at one point and then goes back up like that. Okay, so that's what the graph of this equation must look like, because this equation here, or this inequality here, says that your graph of this function is bigger than or equal to 0. All right, now if we set it equal to 0 and use the quadratic formula, of course we get this for t right here. All right, however, you have at most one solution here for t, right? There's at most one solution. It might be like this value right here. You only have one solution. So what that means is the discriminant right here, this term right here, the square root of b squared minus 4ac, this must equal 0. Well, it's either equal to 0, let me say it like this rather. What you have in here, the b squared minus 4ac, this either has to be, it's either equal to 0, in which case you would have a picture like this, where you have the graph crossing at and hitting the x-axis at one point, or it is negative, in which case you have a picture like this, where you have no real valued solutions. So the discriminant here, b squared minus 4ac, that's what we call it, is definitely less than or equal to 0. Okay, so let's take note of that now. All right, so that's what we have right here now. Okay. Now recall that the b, that was equal to 2 times the inner product of u with v. And the a, that's the uu, and the c was the vv. So this is a, c, and right here we have the b squared. Notice if we square this, we get 4uv squared. Okay, so we have that so we have that this is less than or equal to 0. We can drop these 4's off, right? Just divide them to the other side. 0 divided by 4 is 0. And then let's move this term right here over to the other side, and we end up with this inequality right here. So uv squared is less than or equal to uu times vv. Now just take the square root of both sides. Okay, and when you take the square root of the left-hand side, so if we take the square root here of both sides, this term right here is going to be the absolute value of uv. Remember, the square root of x squared is technically the absolute value of x. So that's what we have right here. And right here we have the square root of the inner product of u with itself times the square root of the inner product of v with itself. Well, this is just the norm of u by definition, and this is just the norm of v. Remember, because the norm of u, that was previously defined to be the inner product of u with itself to the 1/2 power. And we have our result now. This is exactly what we wanted to prove. So it was sort of tricky. We used the quadratic formula to prove that result, and that is a very important result in mathematics. Now let's take a look at a few examples. Now in your readings, just take note of this example right here. It verifies an important inequality in analysis. This inequality right here, so the integral from a to b of the product of two continuous functions, the absolute value of that is less than or equal to the integral from a to b of f squared to the 1/2 power times the integral from a to b of g squared to the 1/2 power. That's actually an important inequality in analysis, and the way you verify it is from the Cauchy-Schwarz inequality. Notice it looks a lot like this inequality right here. Well, that's exactly what it actually is. If we use this as the inner product for f with g. So notice that if we put an f here and a g here and an f here and a g here, that this Cauchy-Schwarz inequality here turns exactly into this inequality right here. So the f comma g is the integral from a to b of f times g. The norm of f is the integral from a to b of f times f to the 1/2 power, and the norm of g is the integral from a to b of g times g to the 1/2 power. So this inequality right here comes directly from the Cauchy-Schwarz inequality. Now let's note something that we had talked about earlier. So recall that for the dot product in R2 and R3. The Cauchy-Schwarz inequality Now let's take a look at something that we had talked about before. Notice that the dot product in R2 and R3, the Cauchy-Schwarz inequality follows easily from this fact right here. Okay, and we mentioned that previously. Now, having proven that this right here, which is our Cauchy-Schwarz inequality, holds for any inner product, what we can do then is rewrite this inequality right here, which is the Cauchy-Schwarz inequality, like this. Remember, if you have the absolute value of a is less than b, right, that's the same as saying that a is less than b and greater than negative b. All right, remember that? And that's exactly what we have right here. Okay, the inner product of u with v is the a, and the right-hand side here is the b. So we have this. And now dividing both sides by the norm of u times the norm of v, we end up with this inequality right here. And now this is important. Remember, we had talked about this before, because now we can define the angle between any two vectors in an inner product space to be the inverse cosine of this quantity right here. Since we now know that this is always going to be between -1 and 1, it makes sense to take the inverse cosine of it. And so that's what we have in this definition right here. So given an inner product space V and any two non-zero vectors u and v, we define the angle between u and v to be the inverse cosine of the inner product of u with v divided by norm u times norm v. And that's it. Remember before, when we had dot products, what this was right here was u dot v. Well, now, since we know this inequality holds for inner products, well, now we can define the angle between any two vectors in any inner product space. All right, let's take a look at an example. So here, let's let V be the vector space of all continuous functions on the interval from 0 to 1, with this notion as our inner product that we had seen before. Let's find the angle between these two functions using this definition as our inner product. All right, so all we have to do is use this formula right here. So we have to calculate the inner product of x squared with x, and that is right here. So that's just the integral from 0 to 1 of x squared times x. That turns out to be 1/4. And then we need to evaluate the norm of x squared and the norm of x. So the norm of x squared is going to be this quantity right here. Notice x squared times x squared. Take the integral, right, and then to the 1/2 power. This integral right here turns out to be 1/5, and so you take the square root, so 1/√5. And then down here we have the norm of x. So that is the integral from 0 to 1 of x times itself to the 1/2 power. You end up with 1/√3. And so therefore the angle between x squared and x is this quantity right here. Notice we have the inner product of x squared with x over norm of x squared times norm of x. You end up with this right here. And so you end up with the inverse cosine of √15/4, which is approximately 0.2527, and that would be in radians. And there you go. All right, now let's take note of this down here. So if we're given any two vectors u and v from an inner product space, notice that from this equation right here, the angle theta is 90 degrees, or pi/2, if and only if what is inside here is equal to 0. And the only way this can equal 0 is if the numerator is equal to 0. And so that leads us to our following definition down here, just like we had for dot products. Given any two vectors u and v from an inner product space, we say that u and v are orthogonal or perpendicular if the inner product of u with v is equal to 0. And that's it. That's all we have to do. Recall when we were dealing with dot products, we had this u dot v was equal to 0. Well, so now what we've done is simply extended this definition to inner product spaces. So here we have a simple example. Let's show that if this is the vector u and this is the vector v, that these are orthogonal with respect to the standard Euclidean inner product. Well, the standard Euclidean inner product is just your dot product, so if we evaluate u dot v, you see you'll get this, and that is equal to 0, so u and v are orthogonal or perpendicular with respect to the Euclidean inner product. Now let's take a look at this example right here as well. So if we consider the vector space of all continuous functions on the closed interval from -1 to 1, with this inner product right here, let's show that x squared and x are orthogonal or perpendicular functions. Sort of strange to think of two functions as being perpendicular, but that's what we can do. Well, so we need to evaluate u comma v right here. So the inner product of x squared with x. Now we're integrating from -1 to 1 instead of 0 to 1 now. So we integrate from -1 to 1 of x squared times x dx. That's the integral from -1 to 1 of x cubed. And if you evaluate this, of course, you will get back 0. So therefore, the angle between x squared and x is pi/2, or those two functions are orthogonal. Now let's take a look at a few theorems down here. Now here's a theorem detailing some important properties of length for any inner product space. First of all, the norm of any vector is bigger than or equal to 0. And the norm is equal to 0 if and only if u is equal to, and that should be the 0 vector right there. This is the 0 scalar, the real number 0. We also have that if you take any scalar k times u and you take the norm, you can move the k outside, but you do have to put absolute values around it. This doesn't mean dot product, that just means times. You have a real number times, and this is going to be a real number. And this property right here is called our triangle inequality. It makes the statement that the norm of u plus v is less than or equal to norm u plus norm v. That's called our triangle inequality because graphically what it looks like is this. If this is u right here and v right here, and we form u plus v, which is going to look like this. Okay, so right here would be u plus v right there. Okay, so you see the length of this side is the same as the length of the vector u, so we have this as being the norm of u. This side right here being the norm of v. And this side right here of the triangle being the norm of u plus v. So you see the length of this side of the triangle is going to be less than or equal to the length of this side plus the length of that side. So that's in the Euclidean inner product, but it's also true for any inner product, which is what we're saying right here. All right, now let's prove parts C and D and leave the rest as exercises. So for part C, notice that the norm of k times u we can write like this. So that's going to be the square root of the inner product of ku with itself. Now by properties of the inner product, we can move this k out and that k out, and we get this. Then we can break the square root up. I don't have the step written in here, but notice that this is the square root of k squared times the square root of the inner product of u with itself. And this term right here is just the absolute value of k. And we end up with our result right here. So that's the proof of C. Let's take a look at the proof of the triangle inequality. So for the triangle inequality, what we're going to do is we're going to square that left-hand side. So notice right here we have the norm of u plus v squared. Now we'll get rid of this soon. Okay, so this is equal to the inner product of u plus v with itself. Now just break this apart using the distributive properties for the inner product, and we get this right here. So sort of like foiling, you know, inner product of u, uv, vu, vv. Okay, and we end up with this. Okay, notice we get the 2 uv comes from uv plus vu, and this right here is equal to uv because we can move them around by the commutative property. Now this term is the norm of u squared. This term is the norm of v squared. And then what we can say is that this quantity right here is going to be less than or equal to, now what we're going to do is take the absolute value of the middle term right here, and that's what we have right here. Okay, and we lose equality. So we have to put less than or equal to here because this could have been a negative number and we made it positive if it were negative. So we then would have an inequality going in this direction. And this right here by the Cauchy-Schwarz inequality is less than or equal to 2 times magnitude u, magnitude v. Okay? And then we can notice that this is equal to norm u plus norm v, the quantity squared. you see what we have here is really sort of just like a squared plus 2ab plus b squared, right? And that's equal to a plus b squared, right? That's what we have. And so now what we can do, so you see we have this is less than or equal to this. That's what we have written right down here, right? Now just take the square root of both sides and you get your result, and you have your triangle inequality for inner product spaces. And there you go. Now let's take a look at some properties of distance. So if u, v, and w are vectors from any inner product space, note this. The distance between u and v is always bigger than or equal to 0. Well, that's true because the norm of any vector, that's the distance, is always bigger than or equal to 0. The distance between u and v is 0 if and only if u equals v. In other words, if and only if what's in here is equal to 0, the 0 vector. And then, of course, you just take v over to the other side. The distance between u and v is equal to the distance between v and u. Well, that's true because you can just flip these around, right? And also using the fact that the norm of u is equal to the norm of negative u. That's a fact as well, because really you have a negative 1 here that can be pulled out, but when you pull it out it would become the absolute value. And then you have this result right here, which is just a restatement of the triangle inequality. Let's actually take a look at the proof of part D, even though I said to leave it as an exercise. So if we start out with the left-hand side here, remember that is just the norm of u minus v. Now what we're going to do is we're going to do a little trick where we add a vector in and subtract it back out. So notice that this is equal to now by the triangle inequality, this is going to be less than or equal to right? And this is equal to, this is your distance between u and w. And this term right here is your distance between v and w, or w and v. Okay, and of course what we started with up here was the distance between u and v right there. Okay, so that proves the triangle inequality. Now we have a definition down here for any inner product space. We actually saw this one before. This is just a restatement. If the inner product of u with v is equal to 0, then u and v are said to be orthogonal or perpendicular. If the norm of a vector u is equal to 1, then u is said to be a unit vector. We've seen that before, but now this is just stated for inner product spaces. And the set of all vectors satisfying this is called the unit circle or unit sphere. So it's the set of all vectors in your vector space that are of length 1. Let's take a look at this proposition. So for any vector u, non-zero vector from an inner product space, if we take u and we divide it by its norm, that is going to be a unit vector. Now keep in mind that this is actually equal to 1 over the norm of u, that's treated like a scalar, times u. That's really what we mean here. Okay? And down here it's a simple proof. Notice that we have here, we want to prove that the length of this vector is 1. So we take its norm and we write it like this. Now this is like your scalar k that can be moved outside. And this is always positive, remember, because the norm of u is always bigger than or equal to 0. So this is positive, so we don't have to take its absolute value. And you see these two obviously cancel, those two numbers, and you get back 1. And that's your proof. All right. So let's take well, here we have another example. I'll let you do that as an exercise. Let's take a look at this one right here. So in R2, with this weighted inner product right here, let's sketch what the unit circle would look like. So all the vectors in R2 that are of length 1, but with respect to this inner product. And then part B, we have another part here. Well, we actually already did part B. Considering U and V as 2 by 1 column vectors like this, verify that the inner product is generated by this matrix. We actually already did that problem previously. So let's take a look at the unit circle for this inner product. So here's our solution for part A. So let's let u equal xy. Instead of u1 and u2, we're going to let it be xy because those are normally the variables that you use when you graph an equation. And setting the norm of u equal to 1, now the norm for this, remember, written like this, it's going to be 1/9 x squared plus 1/4 y squared, right? Okay, that is the norm of this vector, right? That is, remember, that is xy like this to the 1/2 power. And using the inner product that we had stated then previously, you see it's going to be 1/9 x times x plus 1/4 y times y. And then we have to take the square root of all that. And then we set it equal to 1 because we want our norm of u to be 1. So we end up with this equation right here. And now squaring both sides, you end up with this equation right here. And that is the equation of an ellipse. So right here is what the unit circle looks like with respect to that inner product. It's not actually a circle as we know it, it's actually an ellipse. Also notice where we cross the x and y axes here. Notice the x-axis crosses at -3 and 3. That's because if we set the y equal to 0 and we solve 1/9 x squared equals 1, well, we get back x is plus and minus 3. And the same thing if we set x equals 0, we'll get y is plus and minus 2. And so there you go. That takes care of that example.